Now this is a easy problem. Motion of a heavy particle over a smooth sphere. Motion of a heavy particle over a smooth sphere. Now let us say we have a sphere. So this is a hemispherical top surface and friction is 0. So let us say this hemispherical surface is fixed over ground. So this is fixed over ground. Now this is a smooth. So for this surface mu is equals to 0. Now this is the vertical diameter. A particle is kept here initially. That makes an angle alpha with the vertical initially. Now this particle starts, if I simply leave this object, this will start going down. So this object, basically this mass m start going down. At certain point of time this is here. And this makes an angle theta with the vertical. So this radius vector, so this radius makes an angle theta with the vertical. Now I can write equation of motion for this. If you see forces that is acting, one force that is acting is mg. Now you know this side will have, this angle is theta, then this angle is theta, because these are the alternate angle. So this side will have mg cos theta, this side will have mg sin theta. Are you getting? I can make another diagram. So in the tangential direction, so this is your center. Towards center you will have mg cos theta, and in the tangential direction you will have mg sin theta. So these are the forces. Now we have said in the earlier concept, you can write two equations. In the tangential direction there is a radial direction, there is also a force, that is normal reaction. So there is a normal reaction that is also acting. So I can write equation in the radial direction. So force towards center, that is mg cos theta minus n, that is equals to mass into acceleration v square by r. R is the radius of the circle. Now the second equation, that is the tangential equation, I can get in two ways. I can either write equation of motion and then integrate, or I simply write energy conservation. So second equation I can get from energy conservation. So tangential direction equation, so in the tangential direction equation I can get two ways. Either I write equation or I simply do energy conservation. Applying energy conservation is always easy. So let us apply energy conservation in the to find out the tangential equation. So if I apply energy conservation, this surface is smooth, there is no loss of energy. So initial potential energy is, this angle is alpha, so this height is mg s h cos alpha or r cos alpha. So initial potential energy is mg r cos alpha. Initial velocity is 0, so kinetic energy is 0. Now you have finally mgr, and now this angle becomes theta. So this angle is theta. So this becomes mgr cos theta plus, now the velocity here let us say is v, so you will have kinetic energy half m v square. Are you getting or not? So from here you will have, so let us say you will have 2 mgr cos alpha minus cos theta. This is equals to mv square. So this is my equation number 2. If I plug this value in equation number 1, so I can have from equation 1. So let us plug the value of mv square. So I can get normal reaction mg cos theta minus n. This is equals to mv square, that is this value. So 2 mgr cos alpha minus cos theta. This divided by r. So r goes out. So we will have mg cos theta minus n. This is equals to 2 mg cos alpha minus cos theta. Are you getting? I can solve for normal reaction. So this goes this side. So I can write normal reaction is mg cos theta minus mg cos theta minus 2mg cos alpha minus cos theta. So this is the basically normal reaction. You can basically plot this. If you want, you can plot normal reaction with as a function of theta. You see, I want when this surface, this object leaves the surface, at that point of time when breaking off, so this is leaving the surface, normal reaction will be 0. So this is the condition of breaking off. You will have mg cos theta. So this will be mg cos theta. Now mg cos theta minus mg cos theta 2mg, so this becomes 3mg cos theta minus 2mg cos alpha. This is the normal reaction, this is 0. So you can solve from here. So this is cos theta is nothing but mg goes out, so 2 by 3 cos alpha. So this is the condition. So theta will be given by 2 by 3 cos alpha. So at which point this bigger mass will leave the surface, that angle is basically given by cos theta is 2 by 3 cos alpha. So this is the point where this mass will leave the surface. Are you getting or not? So we already said only one important point we have in this question. One point is I can write the radial direction equation, another is to write the tangential equation. Writing equation in the tangential direction is same as doing energy conservation, and it is always advisable do energy conservation without writing the equation of motion in tangential direction, because once you write equation of motion in tangential direction, you integrate, you get the same equation. You can verify yourself. We will do some question in that case also, so that you have verification. So in tangential direction I am not writing the equation of motion, I am using energy conservation, that gives the second same equation with the tangential direction motion. Now radial direction motion I know, a normal reaction terms comes there, and if I plug the value of V square I will get normal reaction. You see, normal reaction is a function of theta. If you want, you can plot normal reaction. You see, normal reaction is basically a function of cos theta. If your theta increases, normal reaction decreases. You have mg and plus, so this is 3mg cos theta minus cos alpha. So normal reaction is a function of cos theta. So theta increases, normal reaction decreases. This means there is a more chance if it goes downward. So this block is coming this side, normal reaction keep decreasing. At one point of time normal reaction becomes 0. At that point of time the object can basically leave the surface. So what is the condition? What will be that alpha and theta condition so that the object can leave the surface? So theta will be given by 2 by 3 cos alpha. Cos theta is basically given by 2 by 3 cos alpha. 2 by 3 into cos alpha. So this is 2 by 3 into cos alpha. We'll discuss the next problem.